Hello everyone, welcome to the last lecture of week 4 of the course Power Network Analysis, in which we will continue our discussion on the fourth main module, which is transmission line parameter evaluation. And in today's discussion, we will try to find expressions for magnetic flux linkages of a conductor with respect to a point because of a group of conductors. So essentially, what we have discussed in till the previous lecture or lectures were evaluation of inductance due to internal flux lines and external flux lines, basically for points outside the conductor, inside the current carrying conductor. So we have evaluated or figured out the expression for inductance for a conductor, single conductor, with respect to internal flux lines, magnetic flux lines, as well as external magnetic flux lines. What we would take up or expand further is how would you find inductance of actual transmission lines, which need not be just one conductor. We have taken or understood one example or initial lecture or first lecture of this module. We understood about ACSR conductors, aluminum conductors with steel reinforced. And aluminum or ACSR conductors, they have strands of steel, they have strands of aluminum wound around the steel strands to increase the mechanical strength. What we have found so far or evaluated so far is probably the inductance of a single strand or a single conductor, that too under certain assumptions. So let's see how in a group of conductors or a group of strands, how the inductance expressions or flux linkage expressions could be evaluated. Because once we know what is the value of lambda, then from there we can also jump or evaluate the corresponding value of inductance. So it need not only be flux linkage, we can also try to go around with finding expressions for stored magnetic energy E, and from there also we can find L. So we'll probably or we will keep our focus on trying to find this lambda from where we can find the corresponding L's. So let's go into what we have. So we'll try to sort of complexify or complicate the case one by one. So earlier our focus was only on one conductor or one strand. Now I am bringing in another conductor which could act as a return conductor for the actual conductor. So the return conductor is carrying current I2, the actual conductor might carry I1, and I1 and I2, their directions have to be different because one conductor is acting as the return for the other conductor. So essentially at any point of time, I2 is always negative of I1, and that's how balanced operation between a single phase 2-wire circuit can be ensured. The directions of these currents, they might change if these currents are AC, or they may remain the same as shown over here. I1 entering into the plane of the slide, whereas I2 is coming out of the plane of the slide if these are DC currents. And the individual conductors or wires or strands, their radiuses are R1 and R2, and the center to center distance is capital D. And the conductors are so spaced or so placed that this distance D is exceptionally large or higher compared to individual resistance, compared to individual radiuses, pardon me for the word resistance, their individual radiuses, so that our idealistic assumptions still hold true. That is, the magnetic flux lines, they still remain concentric, their distribution remains uniform. The current density in respective wires, they also remain uniform. Although the figure shows some distortion, but for our sake of discussion, for simplicity, we will not focus on these distortions as of now. We will still assume these flux lines to be concentric flux lines, and the two conductors are at a large distance. So these flux lines, magnetic flux lines near the conductor space outside the conductor don't get distorted. They still remain concentric. And as I mentioned, current densities are also assuming to be uniform because of this idealistic condition. And flux lines, because of current I1 and I2, as per the symbols or the flows that we have, since I1 is into the plane of the slide, so if by right hand rule, if thumb points into the plane of the slide, the fingers would curl in a clockwise direction. the corresponding magnetic flux lines, they are actually clockwise, whereas for I2, the same flux lines, they appear to be in a anti-clockwise direction. So if we look at the space in between these two conductors, the flux lines, magnetic flux lines, because of individual conductors carrying I1 and I2, the overall magnetic flux lines, they are additive in this space between the radiuses, between the conductors at distance d. So we'll make use of this fact towards the little bit towards the end of today's discussion, that in between the space of these individual conductors, the magnetic flux lines, they are additive, whereas for space apart from the conductors, the corresponding flux lines, they are not additive. So if you focus on this part here, from the space outside the region where we are looking outside the two radiuses or two conductors placed at distance d, the corresponding flux lines, they need not be in the same position. So by Ampere's law, if we draw a surface which is at a distance of d plus r2 more than the center of conductor 1 whose radius is r1. So basically what we are trying to say is, if I draw a surface, let me mark the distance of that surface. That distance is, this distance is given as d, center to center, and this additional distance is r2. If I draw a surface which is just touching the extreme rightmost surface of conductor of radius r2, and this surface is again concentric, thanks to our concentric magnetic flux lines, the surface is concentric, and this surface could be considered as a circle, the dotted circle that I have drawn, whose radius is d plus r2 from the center of conductor carrying current I1. And on this surface, if I were to apply Ampere's law simply says the integral of dot product of magnetic flux intensity and the length vector dl should be equal to the net current which is encompassed inside this surface. Now let's look at this surface which I have considered to be a circle. Inside this circle, there are going to be two conductors. Conductor number 1 is carrying current I1, conductor number 2 is carrying current I2, and since it is a single phase two wire circuit, I1 plus I2 is always 0 because I2 is negative of I1. So inside this surface, even though there are two conductors, the net current at any point of time inside this surface is always 0. So if the MMF itself is 0, that means no matter what distance I take at a distance d plus r2 or more than that, the corresponding Ampere's law simply says, oh, no magnetic flux interactions are, no meaningful magnetic flux interactions are going to happen for this single phase two wire circuit. So that's the reason why it is mentioned that the flux line set up by current I1 at a distance d plus r2 from the center of conductor does not link the conductor 2, because the net current inside this surface is always 0 because of I1 plus I2 being equal to 0. Same could also be said for flux lines with respect to current I2 at a distance d plus r1 from the center of conductor I2. The corresponding net current will again be 0, so no MMF would actually result in. So at a distance, only at a distance less than d, the corresponding, since we are assuming the current densities to be uniform in both the surfaces, so for, and also d is much more than individual radiuses. So essentially at a distance around d, or to be precise, d plus r2 less than that particular distance, the flux lines of conductor 1 are linking the current I2 in some fashion, in some manner as per Ampere's law. And since d plus r2 or d minus r2 is approximately equal to d, because d is much larger than r2 and r1, so that's where this distance d is coming into consideration. So if we apply the logic of net inductance at a point d from the center of conductor carrying current I1 with radius r1, then the inductance between point which is the center of conductor, let's say point A, at a distance B, which is just outside the surface of conductor carrying current I2, would be nothing but d L1 equal to 2 into 10 power minus 7 as per the expressions that we saw in the previous lecture, considering that mu r is equal to 1, because in between these two spaces we have essentially air or vacuum, and relative permeability of air is equal to 1. So we have this simple expression, which is the inductance of circuit due to current I1. Similar inductance will also exist because of current I2. These inductance expressions, they are independent of current, so their values don't affect, but individual radiuses, yes, they might be same, they might be different, and mu r here is the relative permeability of the conductor, not the air. For air, the relative permeability is exactly equal to 1. And since the space between these two conductors, the MMFs or the flux lines, they are perfectly additive, as we have discussed earlier. So we can find the overall inductance, which is addition of L1 and L2 for the entire circuit, which is the single phase 2-wire circuit, and we get this expression as our overall expression. How do I get this expression? It's pretty simple. So if I if I have to sort of evaluate or cross check this, then L1 plus L2 is ln of 2 into 10 power minus 7 natural log of d by r1 dash plus natural log of d by r2 dash with the entire factor 2 into 10 power minus 7 outside. This can be rewritten as 2 into 10 power minus 7. Sum of two logs with common base is also equal to log of the product of these two arguments of logs. So basically I have d square by r1 dash into r2 dash, which can also be rewritten as 4 into 10 to the power minus 7 divided into 1 by 2 natural log of d square by r1 dash r2 dash. This term is nothing but the term present over here, and 4 into 10 to the power minus 7 is the term present over here. That's how we get our overall inductance for the single phase 2-wire circuit as Henry per meter, because we are considering the length of these two conductors to be on a per unit length basis. Essentially, it is equal to 1 meter. If the per unit length is 1 kilometer, 1 mile, then corresponding distance units could be km or mile as per the line per unit length that we are considering. Moving on to a set of conductors, or basically we are complicating the situation more and more. Earlier we focused on only 2 strands or 2 conductors. Now we are focusing on n number of strands or n number of conductors, because actual ACSR conductors are made up of different strands, and the number need not be only 1, they can be more than 1. And since these strands, in this set of strands or conductors, we have our assumption that at least one of those conductors is acting as a return conductor for the entire circuit. So that is the reason, the way in the previous discussion of single phase 2-wire circuit, I1 plus I2 was equal to 0 at every point of time. In a group of conductors also, we are not specifically pinpointing which conductor is acting as a return conductor, but the overall sum of all these instantaneous currents, these could be AC currents, DC currents, their sum is always 0. So there may be one or more than one conductors which could be acting as return conductors for this entire bunch of conductors. So given this condition, let us try to find the flux linkage of one conductor with respect to a point P, because of all these individual current carrying conductors carrying current I1, I2, In. Their radiuses might also be different, which could be R1, R2 till Rn. We will, for our sake of discussion, have a simple notation, and we'll again reuse this aspect that overall flux linkage. We have seen this expression. It is nothing but mu naught I by 2 pi natural log of d2 by d1, where d2 and d1 are 2 points outside a current carrying conductor of strength of current I basically. So we'll reuse this and try to find the corresponding flux linkage. So let's do that one by one. So if I have a point P which is at a distance d1p from the center of conductor carrying current I1, it is also at a distance d2p from the center of conductor carrying current I2, similarly D3P, D4P, and goes on till DNP, where I1 plus I2 plus I3 till IN, they are all 0 at any point of time. And if I focus only on one conductor at a time, so let's focus only on current I1. For current I1, we have seen that the net inductance or net flux linkage, basically looking at flux linkages here, net flux linkage at a point P from the center of the conductor, which is the distance being D1P, due to current I1 is nothing but this expression here, where lambda 1P essentially indicates current, indicates the points, which is 1 here is representing center of conductor carrying current I1, P is the point of concern from with respect to which the flux linkage is being evaluated, and comma 1, this comma 1 could become comma 2, comma 3, comma n, is indicating this flux linkage we are evaluating is because of which current. So comma 1 here is indicating that this flux linkage is because of current I1. And the remaining terms, I believe it's pretty obvious or understood by now, since we're talking about individual conductors. So current I1 and the current center of conductor I1, they are related by R1 dash, where R1 dash is R1 to the power minus mu r by 4, mu r being the relative permeability of conductor carrying current I1. So similarly, if we now try to find lambda 1p comma 2, lambda 1p comma 2 is the flux linkage at point P with respect to center of conductor carrying current I1 due to current I2. So going by the same expression given over here, if we have to find lambda 1p comma 2, it would be nothing but mu naught I2 by 2 pi natural log of the denominator distance is the distance between the first number sitting over here and, pardon me, the first distance in the natural log denominator 1 comma p comma 2 is the distance between the second point P and the current which is responsible. So basically this would be D2P divided by the distance between the first current, the first number, and the second current I2. So basically it would be D21. Now D21 is the center to center distance between these conductors, which is mentioned over here. So if we go on and try to find flux linkages because of other current carrying conductors, so this would be the individual expressions that we would get. And since our focus is between center of conductor carrying current I1 and point P, so individual flux linkages, we can add them up because these are actually components of the same flux linkage because of different currents. So if you want to find the total flux linkage, we can add up these flux linkages, and since we know that instantaneous sum of currents, all currents is equal to 0 because this is a net zero arrangement of conductors. So if we reuse this expression, or basically if we replace I of n by this negative sum present over here, then we get two distinct terms or two distinct components. So let's look at those two distinct components. So what I have done here is the first two expressions, they remain the same, and I have broken up their corresponding natural log numerators and denominators separately. So essentially I have one term which is the sum of all natural log numerators with respective currents. The other sum is basically, since log of 1 by r is equal to log of 1 minus log of r being 0, so this term is also minus log of r. So the corresponding natural log denominators, they are represented by this expression here, which is the denominator terms with respective current components. And from here, I replace I of n as minus of I1 plus I2 goes on till I of n minus 1. So if I put that or do that, then what do I get? I am putting this substitution only in this term. So if I do that, then if I focus only on the first addition, I'll have I1 log of D1P, and the other term which would come from over here is minus I1 log of dNP. I can combine these two and write it as natural log of d1p by dNP, which is what you are seeing over here. Similar terms could also come in for other expressions, and in this expression what we see here is that after substitution of this current In into the expressions here, we are now getting ratios of distances of point P from individual centers. Now think of the fact that if this point P tends towards infinity, that means point P is being stretched out and it's going far off from this conductor arrangement. Don't you think that the individual distances, that is d1p, d2p, d3p, dnp, they would more or less tend to be equal to each other? If not equal, their differences would become marginally so small, because point P is at a point is very far off from this arrangement of conductors. So essentially, the point P tending to infinity, we would have this particular condition where individual distances become more or less similar, and if individual distances become more or less similar, then this number here inside the natural log term would start tending to 1. In fact, all these distances would start tending to 1 individually, and we also know that natural log of 1 is always 0. So essentially, we would have the first terms, which are over here, all individually tending to 0, and we would only be left with the negative term sitting down inside, and that's how lambda 1 infinity is minus mu naught by 2 pi, sum of individual self radiuses and the distance to distance radius, the distance to distance center points, and the corresponding current components. This is essentially the flux linkage of one conductor in a group of conductor N, whose instantaneous sum of currents is always 0. Build up our next discussion on the basis of this particular flux linkage. So in case if you have any doubt or confusion regarding this, I would request all the viewers to please revisit or go back a couple of minutes ago in this particular discussion to again recheck whether the numbers or the expressions that we are getting are actually correct or not. Beyond this, after this, we will build up our next discussion based on the expression that we are getting here. So now, and again, as I mentioned, similar flux linkage expressions could also be obtained for other conductors with respect to point P tending to infinity. Now let's go to a relatively much more complicated case where we talk about composite conductors. Composite conductors are nothing but the ACSI conductors that we saw in the first lecture of this particular module, where practical transmission lines have multiple strands, and depending on the voltage level, they could have different bundles. Bundled part we will come discuss later, not today, or not in today's discussion. We'll focus only on stranded conductors or composite conductors. There could be several conductors which are containing several strands in parallel to each other for even a single phase circuit or for a three-phase circuit. Both could be applicable. We are focusing on a single phase arrangement where one set of composite conductor, one conductor, which is composite conductor A, is having different strands. Those strands are labeled from A to N. So you could also define your own label. So for my reference, I am choosing composite conductor A to be carrying to be containing strands whose numbers or labels could be from A, B, C till small n. Small n is the number important here. And composite conductor B is also having strands which could be labeled as A dash, B dash, C dash, so on. So basically this set here is a set of n alphabets or n numbers, and similarly composite conductor B is also having different strands with different labels of total number of number m. And we are talking about an arrangement where these two composite conductors refer to a single phase circuit, and that's the reason why one composite conductor is acting as return path of the other conductor. So essentially, if I have to take the net sum of current of all conductors, so IA plus IB plus IC, which is the sum of currents of composite conductors present over here, and add them up with the currents of A dash, B dash, IC dash, etc., etc., the instantaneous sums, they would always turn out to be 0. And for sake of our simplicity in discussion, we are assuming individual currents in composite conductor A to be equal to carrying current I by N. The current distribution is uniform. And since the sum of currents is always 0, so if I is the net current in composite conductor A, definitely composite conductor B would carry current minus I because of this relationship, and current distribution being same or uniform. So minus I by M is the individual current in the individual strands of this composite conductor B. Our assumptions remain the same. They are idealistic assumptions that the strands are all similar with similar radiuses and diameter. Magnetic flux lines are concentric, current density is uniform, no distortion is happening, and perfect concentric flux lines, magnetic flux lines exist. There are no distortions. So if we apply our logic of flux linkage expression, which we saw over here, over to the flux linkage evaluation in this set of composite conductors A and B, where we could have different strands. So the way we focused on one strand and tried to evaluate inductance with respect to its own current as well as currents because of other strands. So if we use that, then the flux linkage would have two distinct terms. The first term would be because of flux linkage of conductor A in composite conductor capital A, which would have two terms. One term would come because of the strands present in conductor A. Each of these strands are carrying current I by N. So if we have two natural logs, let's say x log of z plus x log of y, it is equal to x log of z comma y. So we use this property, and that's how we get this expression. Similarly, the other conductor, composite conductor B, is having strands which are carrying currents minus I by M, and the corresponding d distances that you see are the pairwise distances between individual strands. So we have the second term because of composite conductor B. And if we now rearrange this a bit, this is what would be the flux linkage of conductor A, net flux linkage of conductor A with respect to a point P which is at infinity because of all individual strands. And dA is the effective self radius of conductor A itself. Thus, all conductors have the same radius, so R remains same for all of them. Their material property is also same, the relative permeability is also same. Similarly, if we now try to find the inductance expression of conductor A, which is carrying current I by N, so LA would be nothing but flux linkage divided by the actual current. So we get the expression of inductance here. This expression looks very complex, looks very difficult to evaluate. Please have patience. We will first understand, and I mean this understanding is important of how the expressions come in, and then we would find simpler ways of how actual inductance expressions can be evaluated while trying to minimize the complexity of evaluating these distances, taking their 1 by mth root or the mth root. 1 by m is the mth root of the expression here, whereas 1 by n is the nth root of this particular denominator product or distance product. So, similar inductance expression we can also find for strand B in composite conductor A. We can also find similar inductance expression for any other strand in this entire composite conductor A or B. And if we start doing that, we can find, as I mentioned, we can find the inductance of any other strand in the composite conductors A or B. The average inductance, if we were to sort of average out or normalize these individual inductances, because the distances are going to be different here. So for LB, if you see, and for LA, if you see, the individual distances, they are going to be different because that depends on the spacing between the strands, how a CSI conductor is arranged, how these two ACSR conductors, one return, one live, are also arranged. The distances might be different. So individual LA, LB, LC could also be different. In order to normalize this individual strand effect for the entire composite conductor perspective, what we can do is we can average out these individual inductances, and probably that average would be associated as the average inductance of any strand in conductor A, which would be sum of individual inductances in strands in composite conductor A divided by the number of strands that are present in the composite conductor A. So if we substitute those expressions, the overall expression becomes further more complex and becomes much more boggling. Please have patience. We will rebuild our discussion of how this could be simplified, or are there simpler ways of finding these complex distances, which we will definitely take up in our next discussion, wherein we will start with evaluation of inductance for actual three-phase lines, where three-phase lines would also have composite conductors, they would also have bundled conductors, and our discussion would build up on the expression that we obtained here. So please revise, check, or browse back this particular video for again going through the concepts clearly. Thank you.